In this video, I'm going to describe to you in detail how OPC UA client-server communication works. This video is sponsored by HiveMQ, the providers of an enterprise-grade, edge and cloud-based MQTT broker, and Opto22, manufacturers of reliable industrial controllers for automation and IIoT applications. Please do check them out on the description to help support this channel. My name is Kudzai Manditereza with Industry40.tv, and I regularly publish Industrial Internet of Things tutorials on this channel. So if you're new here, make sure you subscribe and click on the notification bell to make sure that you never miss any of the videos. In the previous videos, I described how OPC UA information modeling works, and I demonstrated how to create an OPC UA server and client. Now the question is, how does an OPC UA client consume information from an OPC UA server? Now, to answer that question, let us begin by looking at the overall communication architecture that OPC UA uses. So let's take, for example, a manufacturing organization whose main goal is to manufacture and provide customers with finished products as efficiently as possible. In order to achieve that goal, they will need to bring together many different components, from factory floor devices to machines, robots, SCADA, MES and ERP systems, and so forth. And for these components to successfully work together to achieve that goal, they would have to be able to easily exchange information and instructions. So how do we make sure of that? We could start by first realizing that each component in this factory is actually providing a service, whether it is the robotic arm stacking cases of goods onto a pallet, or the MES tracking and documenting all the activities. And then after that, accept the fact that, for example, the internal logic of how the robotic arm performs its job doesn't need to be understood in detail by other components. In fact, all the internal functions of the robotic arm can be abstracted away. What could be exposed to other components instead is a list of functions or services that the robotic arm can perform, and instructions on how other components can invoke those services. This kind of communication architecture that seeks to coordinate operations towards a common goal by having participating components provide services to each other in this way is called a service-oriented architecture. And it is what OPC UA communication is based on. OPC UA provides this service-oriented architecture for industrial applications by defining abstract services such as read, write, browse, subscribe, and method calls to expose the underlying device or equipment functionality, such that when industrial equipment and application vendors implement OPC UA on their products, they are in essence abstracting the internal workings and only exposing a standardized interface for reading and writing to them through OPC UA services. Now, this enables a wide range of industrial systems from different vendors to seamlessly exchange information without having to understand internal information like registers, commands, etc., which is something that has traditionally been difficult to achieve with industrial automation technologies like Modbus, Profibus, and DeviceNet, etc. Now, think about it. Production procedures are normally executed, for example, by having sensors provide input into a controller, which then sends an appropriate signal to an actuator in a hardwired control loop. And if, say, a customer has product requirements that fall outside of the standard production procedure, then you'd have to stop production and reconfigure the production equipment involved, and sometimes reprogram the PLC. So what an OPC UA-based service-oriented architecture enables is an opportunity for external systems to call a machine's methods or services in order to instruct it to do something, which makes production reconfiguration automated, easier, and faster. This reconfiguration interface extends to IT and business software that are outside of the control system domain, which allows control loops to be driven by a business context, a scenario that some would call IT-OT convergence. In a nutshell, an OPC UA server provides methods or services that an OPC UA client can call when it wishes to access the data or send instructions to the server. And to facilitate that interaction, OPC UA has a mechanism
that enables clients to discover Opus UA servers locally or on a network, interrogate them to find out what services they offer, connect to them, use their services, and then disconnect after that. Now, the service-oriented architecture of Opus UA is built on different logical levels. All Opus UA services are abstract method descriptions that are defined at one level, while the data transportation and encoding mechanisms are defined at a separate level. What this means is that it is left up to the Opus UA technology stack developers to map these defined services onto a transport protocol of their choice using Opus UA technology mapping, which we'll discuss later in this series. And then the interfacing of the Opus UA communication stack with user application code is left to the programming environment and SDK developers. And as you may have guessed, this separation of concerns is meant to future-proof the Opus UA standard so that it is not reliant on any one transportation mechanism. Now, Opus UA services are based on a request-response form of communication, which means that for an exchange of information to occur, there needs to be two participants, a client and a server, whereby the client is responsible for initiating communication. So, when a client is interested in reading data from a server, it sends a request, the server processes the request, and then returns a response. Now, let us understand what really goes on under the hood for this exchange of information to happen. To emphasize, both the device or application acting as an Opus UA client and the device or application acting as an Opus UA server need to implement an Opus UA communication stack. This implementation could be in C, C++, Java, Node.js, or .NET. However, as an application developer, you won't have to deal with the underlying stack. Instead, you send and receive messages via an API or SDK. The role of the Opus UA communication stack in this case is to encode and decode those message requests and responses. But here's the thing, it doesn't matter that, for example, the server is using a .NET Opus UA stack while the client is using a Node.js stack. The only requirement is that they both must be using the same technology for transporting the messages. Now, the process begins in the Opus UA user application code, whereby the client uses an Opus UA SDK or API to submit a service request, for example, a read service request. And as mentioned earlier, Opus UA doesn't specify how SDKs or APIs must interface with the user application code. But ordinarily, SDKs or APIs provide methods that correspond to the specification. Now, moving on, the Opus UA stack accepts the service request, encodes it in a message format that conforms to the Opus UA specification for exchanging data on the wire, and then transfers the service request to the server-side stack using a transportation mechanism common to both stacks. We'll discuss shortly how an Opus UA client figures out the transportation mechanism to use. Now, on the other end, the Opus UA server receives the service request, decodes it, locates the service to execute, performs the requested operation, and then sends a response message together with the status of the operation. Now, in order to reduce the number of request-response operations, Opus UA services are designed for exchanging bulk data, whereby you can request more than one variable at a time. You could request one piece of data at a time, but Opus UA provides you with the bulk data transfer option to optimize your service calls. Here's an example of a C# code using the Unified Automation Opus UA.NET SDK to read bulk data. Here we first build a list of nodes to read, invoke the read method, and then get a list of results. And like most communication mechanisms, whereby whenever a service request is submitted, it must be accompanied by additional information to provide the context of the request in the form of a request header, with the server providing context to its response using a response header. An Opus UA service request has a request header, while its service response has a response header. The parameters provided on a request header include an authentication token, which is a secret identifier used by the client to verify that the service request is associated with the current communication session. Then there is a request handle parameter, which is an integer ID defined by the client to refer to its own service call. This client-defined handle can be used to cancel the request. Next, there is a timestamp, which is the time at which the client sent the request in UTC format, followed by the return diagnostic parameter, which is used to instruct the server to return diagnostic information in addition to a status code in the case of an error. And then there is also the timeout hint, which is the timeout in milliseconds that is set by the client for each call. This timeout is used by the server to cancel long-running service requests. And lastly, there is the audit entry ID parameter, which is a string used to identify the client that initiated the action. This is used for security audit purposes. Now, the parameters provided on a response header include a service result, which is a status code indicating the result of the service invocation. And there is also the request handle parameter, which is defined by the client in its request header when it submits a service request. Next, there is a timestamp, which is the time at which the server sent the response. And then there is also the service diagnostics, which is diagnostic information requested by the client. Now, because the primary purpose of OPC UA is to enable interoperability between systems from different vendors, there is likely to be errors resulting from wrong implementation or mere communication errors. Hence, OPC UA services place importance in error handling. So, to indicate the outcome of an operation, OPC UA services issues a service result via the response header as outlined earlier. And the type of that service result is a 32-bit unsigned integer called a status code. The top 16 bits represent a value that is used for specifying the type of error or condition. And the bottom 16 bits are bit flags that contain additional information. Now, the first 2 bits of the top 16 bits indicates whether the status code represents a good, bad, or uncertain condition, whereby 00 indicates that the operation was successful, which is good. 01 indicates that the operation was partially successful and that associated results might not be suitable for some purposes, which is an uncertain warning. And 10 indicates that the operation failed and any associated result cannot be used, which is a bad failure. And 11 is reserved for future use and it should be treated as bad. Now, a key aspect of OPC UA services is the fact that they are stateful as opposed to being stateless. An example of a stateless service is RESTful Web Services communication. Now, to successfully establish a stateful and secure connection between a client and server, OPC UA needs to create and maintain communication at different levels. First, the transport channel for exchanging messages, followed by the creation of a secure channel to secure the messages between client and server, and then a session channel which holds the information about the status of a client during communication. But again, as an OPC UA application developer, you won't have to worry about the transport and secure channels as these are completely handled by the OPC UA communication stack. You just have to create a session and manage its activities in your OPC UA application. And as mentioned earlier, clients may pass a user identity token to the OPC UA server for it to verify that the user is allowed to access the server and what resources it is authorized to use. Now, before we move on, I have to mention that there are projects that aim to provide a REST interface between OPC UA servers and clients that have no knowledge about OPC UA specification, such as apps and IoT devices. The communication is stateless and no session must be maintained between clients and servers. I'll provide the link to the GitHub project in the description below in case you're interested in checking it out. Okay, moving on. Let us now look at the actual OPC UA services used for client-server communication. Altogether, OPC UA defines 37 services, and I'm going to summarize them for you in this video. And for a detailed description of these services, you can check out the complete UA Part 4 specification, which is also linked in the description below. So, all services that are related to each other are bundled together in groups called service sets. This grouping is just for categorization only and has no influence on how each individual service is implemented.
And for example code of these services, I'm going to show you SDK code for Open62541 libraries. Open62541 is an open source and free implementation of OPC UA written in C and C++. I'll also provide a link to their website in the description below.
So the first one is the discovery service set. Now, as highlighted earlier, before an OPC UA client can start exchanging information with an OPC UA server, it has to establish a communication session. And to do that, the client needs to first find out what OPC UA servers are available for connection. And to allow clients to connect to them, servers implement what are called connection endpoints, which are URL network addresses that allow clients to access services provided by the server. And there are generally two types of endpoints implemented by an OPC UA server. There is a session endpoint, and then there is a discovery endpoint, which is a URL address used by OPC UA to offer clients a way of interrogating the server to find out how many session endpoints it has got, what are the transportation protocols available to choose from, what services does it expose, and what security policies does it support, and so forth. This process of finding out the OPC UA server session endpoints and services it offers is called OPC UA discovery. We'll dive deep into OPC UA discovery in a later video. But in a nutshell, an OPC UA server offers discovery services using what is called a discovery server. An OPC UA server can either implement a discovery server within itself, or it can employ an external discovery server called a local discovery server, which runs on a well-known port. So, how it works is that on startup, an OPC UA server would register its session endpoints URLs with the local discovery server via this well-known port 4840. And then when clients need to initiate communication, they can connect to the local discovery server, get a list of available OPC UA servers, and then request session endpoints from a server of interest. Now, this whole process of servers registering themselves and clients finding them, and consequently their session endpoints, is accomplished using OPC UA services which fall into the category called Discovery Service Set. The first service under the Discovery Service Set is the Find Servers service. This service returns a server's session endpoint when implemented by an OPC UA server, and it returns a list of registered servers when implemented by a local discovery server. Next, we have the Find Servers on Network service, which is the same as Find Servers service, with the difference being that it is only implemented by a local discovery server. And then we have got the Get Endpoints service, which is implemented by an OPC UA server. When it is called, it returns the session endpoints supported by the server, followed by the Register Server service, which is implemented by discovery servers and is called by OPC UA servers when they need to register themselves with a discovery server. Finally, we have the Register To service, which extends the registration information from Register Server with information necessary for Find Servers on Network. Now, to create a secure channel, a set of services that fall under the Secure Channel Service Set are used. And as mentioned earlier, these are handled by the underlying UA stack and not on the OPC UA client or server application level. The two services in this category are the Open Secure Channel and Closed Secure Channel services. And then, to create a session channel, a set of services that fall under the Session Service Set are used. Basically, these are services used to establish rules for communication between client and server at OPC UA application level. First, let's look at the Create Session service. When a client wants to create a session with a server, it uses the Create Session method to call the service, to which the server responds with a unique session ID and authentication token, which the client uses for the following calls to the server for the duration of that session. Now, a session is not active until the client calls the Activate Session service successfully. The Activate Session service is used to prove the possession of identification tokens provided by the server and also to provide relevant security certificates. And then, to terminate a session channel, the client calls the Close Session service. Finally, if there are some service requests that the client placed but no longer requires them, the client can cancel those using the cancel session service. Now, if a client needs to add or delete nodes and references from an OPC UA server's address space, it can do so using services that fall under the node management service set. A node can be added to the OPC UA server's address space hierarchy using add nodes service. References can be added to one or more nodes using the add references service, and to delete one or more nodes from an OPC UA server's address space, a client uses the delete nodes service. And then finally, to delete one or more references of a node, a client uses the delete references service. Now, if you remember from previous videos, OPC UA's information modeling capabilities allows it to expose the information of the underlying asset using its address space. So, for the client to consume that information, it has to be able to navigate the address space and read the information. Now, the services used to access the information provided by the OPC UA server fall under the view service set, a view being a subset of the address space created by the server. Now, for the client to navigate through an OPC UA server's address space, it uses the browse service. Now, there are some instances where a browse call response is too large to be sent in a single response. So, when that happens, clients can use the browse next service to continue a browse started with the browse service so that it can get another set of browse information. Now, suppose an OPC UA server exposes a pump object of pump type named pump1, and the client needs to access the speed and on-off status of the pump. The client would need to know the node IDs of these two components in order to access them. And to get those node IDs, an OPC UA client would need to call a translate browse path to node IDs service and specify the node ID of pump1 as starting node and the browse name of the pump speed as the browse path. Now, there are some nodes on the server that an OPC UA client may need to access repeatedly. The register node service enables optimization of such scenarios by reducing the amount of data that needs to be sent each time to access this information. This is done by the server retaining a numeric node ID that the client can use in the following calls instead of using a full node ID. And lastly, the unregister node service allows the client to unregister nodes that have been obtained via the register node service. The query service set allows the client to issue a query to a server, which allows it to access an OPC UA server's data store without having to know the underlying storage mechanism. Services used in this service set are the query first and query next, with the latter used to request the next set of query results. Perhaps the most important feature is to be able to read and write information to an OPC UA server, and the attribute service set is a category of services that enables a client to access the attributes of a node for reading and writing purposes. The read service is used to read one or more attributes of one or more nodes. It is optimized for bulk read operations and not for reading single attribute values. And then we have the write service, which is used to write one or more attributes of one or more nodes. Then the history read service is used to read historical values or events of one or more nodes, while the history update service is used to update historical values or events of one or more nodes. Now, OPC UA's server objects expose function calls as methods, and the method service set provides services used to invoke the methods. The call service is used by a client to invoke a list of methods. This service provides for passing input and output arguments to and from a method. Moving on to the next service set, the monitored item service set defines services that allow clients to create, modify, and delete monitored items used to monitor attributes for value changes and objects for events. The create monitored item service is used to create and add one or more monitored items to a subscription, and the modify monitored item service is used to modify monitored items of a subscription. Next, we have the set monitoring mode service, which is used to set the monitoring mode for one or more monitored items of a subscription. The set triggering service is used to create and delete triggering links for a triggering item. And the delete monitored item service is used to remove one or more monitored items of a subscription. Now, in OPC UA, subscriptions are entities that issue notification messages periodically for the monitoring items assigned to them. The create subscription service set is used to create a subscription, and the modify subscription service is used to modify a subscription. Next, the set publishing mode service is used to enable sending of notifications on one or more subscriptions. Now, the publish service is used for two purposes. First, it is used to acknowledge the receipt of notification messages for one or more subscriptions. Second, it is used to request the server to return a notification message or a keep alive message. And then, the republish service requests the subscription to republish a notification message from its retransmission. The transfer subscription service is used to transfer a subscription and its monitored items from one session to another. And then finally, the delete subscription service is invoked to delete one or more subscriptions that belong to the client's session.
That brings us to the end of this video. Thanks for watching. If you found this video useful, please give it a thumbs up and don't forget to share it with your connections.